Hello and welcome to lecture 3 of Dynamics of Circular Motion, and in this one we're going to be looking at how sometimes your brain is tricked into thinking there are forces acting on you that really aren't there, and we'll see another trick that friction can play. So here is this problem of the bottle on the end of the string going around on a string attached to my finger that we saw last lecture, and I commented then that this one was sort of tough to solve. And so I'm not going to completely solve it this time, but I am going to get it to the point where you can see that it can be solved. And what we're going to look for is the tension. And so that means both its magnitude and direction. So we'll need the magnitude of this vector, and we'll need this angle theta. And I will work it to the point where if you're in my course, you'll see that it's solvable, and you can expect something similar to this on your assignment. If you're not in my course, then consider this an exercise left to the reader to finish the solution. So, as usual, we're going to write Newton's second law out, and so here I go. I'll have some Ftx, the x component of the tension, and that is the only horizontal force. That is ma, the whole a, right, because F net is horizontal, and so the acceleration is horizontal. In the y component, I have the y component of the tension minus the weight equals, and 0, because there is no y component to F net. And now I've done the trig out over here, so we can rewrite this. Ft cos theta, here's the x component, equals m, and I'm going to rewrite a as v squared over r because this is uniform circular motion, and so I can do that. And the y component becomes ft sine theta equals, and I'll take the weight over to the other side and write it as mg. And if you count unknowns, you'll notice we don't know ft, we don't know theta, we don't know v, and we also don't know r. We know this L, the length of the string, but this r here we don't know. Now we'll be able to write an expression for it easily, but at the moment that's where we are. So if you just look at the diagram of the string, you can see that you can get r straight from trigonometry. It is L cos theta. And so once again, r is an unknown, theta is an unknown, but L is known. The other thing we can do is rewrite v. As we've seen, for uniform circular motion, it is the circumference over the period. And we know the period. And so at that point, we now have 1, 2, 3, 4 unknowns, but we have 4 equations, and so this is solvable. I want to compare these two situations that we've seen. They look very different, but they turn out to be almost the same. So the first one was Alice and Bob, some number of lectures ago. Remember, there was the box on the scale in the elevator, and the elevator was accelerating up. And we're going to compare that with the car going through this valley. So if you think about this box, remember that the scale reads heavy, and it turned out to read 150 newtons. Now just realize, if it was reading in kilograms, what does that mean? Well, stationary, that scale would read 10 kilograms. And that's when it is measuring a force, a normal force exerted on it, of 100 newtons. So in the elevator, then, it reads 15 kilograms. And so it comes out heavy. Similarly, in the car, let's say instead of the car, we think about you, right? When you're driving, I know you have a bathroom scale along, and you probably sit on it, doesn't everybody? And in this situation, that bathroom scale would read heavy. Your free body diagram would look just like the car's free body diagram. Your weight and this normal force due to the scale. And so if you have a mass of 60 kilograms, and you work this out, you find that the normal force comes out to 960 newtons if you plug all these numbers in with your mass of 60 kilograms. Now, again, normally in the stationary situation, right, standing on that scale in your bathroom, it reads 60 kilograms when it measures a normal force on it of 600 newtons. And so that means in the car, it is reading 96 kilograms, and so it reads heavy. And so think about what you feel in these situations. In the car, you feel pressed into your seat as you go through the bottom. In the elevator, you feel your feet pressing harder onto the floor of the elevator. And so you literally feel heavy. We call normal forces in this situation apparent weight, because the way you judge your weight, or the way your brain judges your weight, is by feeling the normal forces exerted on you to support you. And so these situations literally fool you into feeling heavier than you really are. So here's a great video where these guys are playing with perspective, and I'll post a link to this video as well as a link to the video about how they're doing these tricks. But they're creating little optical illusions. And if you look at them, you can probably figure out what's going on. They're using perspective to create illusions. And the point is that your brain, in processing visual data, makes assumptions about the sizes of things. And usually those assumptions are valid. But you can fool your brain by creating unexpected perspectives using objects that are of unexpected sizes, like that bench. Well, you can do the same thing with forces. You can fool your body into thinking that there are forces that don't exist by putting it into perspectives, or in other words, frames of reference, that are accelerating. Probably the most familiar example of one of these force illusions is when you're going around a corner in a car. And you've all experienced this. If you are in the car, then as you go around the corner, you feel as if you are thrown to the outside of the curve. Now, as we've been discussing, what's actually happening is that you're being accelerated in. But the thing is that if the seat belt and the friction with the seat, and perhaps in extreme cases a normal force due to the door, didn't stop you, you would go in a straight line, and the car would accelerate without you. But the way your brain tends to interpret this is that it interprets the car as stationary, and so the fact that you feel yourself thrown to the outside of the curve relative to the car gets turned by your brain into a sensation of a force acting that way, when in fact there is no such force. This is a force illusion caused by you being in an accelerating reference frame. This gets called a centrifugal force, and it's a fictitious force in the sense that there's no agent causing any force. A force doesn't really exist. It's an artifact of being in an accelerating reference frame. And if you take a very advanced mechanics course, you may learn how to use axes in an accelerating reference frame and compensate by introducing this fictitious force, the centrifugal force. But in this course, we'll always work in axes fixed to the ground so that our axes are not accelerating, so that we don't have to deal with these fictitious forces. Here's a very standard situation that is going to illustrate one more thing about circular motion, and also is going to illustrate that friction still has some tricks up its sleeves. So here's a car rounding a bend, and the bend has a radius of 75 meters, and what we would like to know is how fast the car can safely go to get around this corner. And so I'm going to again adopt this perspective where the car is going, I'll say, into the page. So V is into the page, and the center of the circle then is that way. And now I'll draw the free body diagram, and all we should have is the weight and the normal. And assuming the tires do not skid, we will have a static friction. And now thinking about which way the static friction points is tricky. I'm going to first say one thing we know is that F net must point in. And now if you're used to thinking about static frictions, you will realize, given that it is the only other force that we can possibly have on the free body diagram, it must point into the circle, which might strike you as a little strange, but just think, if it wasn't for friction, the car would slip and would not be able to go around the corner. So the static friction must be the thing that is actually pulling into the center and allowing the car to round the curve. If we want the max speed, then we are on the verge of slipping. And that means that our Fs is Fs max, which we've seen is mu Sn. And I'll just quickly say this is one of these cases where we're on a horizontal surface, and so mu Sn is just mu Smg. And so all I now need to do is define my axes, and I will put the x-axis in. And so all I now have in the x-axis is that I have the friction, which I've just said is mu Smg, and that equals ma. And I can substitute in for a. So mu Smg is m, and a is v squared over r. And now notice, the masses cancel, which is interesting. It doesn't matter what the mass of the car is, the maximum speed will be the same. And we are basically done. V, this is our maximum v, and it is the square root of mu Sg r, which if you plug into your calculator with the mu s I've quoted here and that radius, comes out as about 26 meters per second, right? So you wouldn't want to put a curve this tight on a major highway where the speed limit is more like 30 or 35 meters per second. And this is a sort of consideration that goes into road design. Just as one last little demonstration, here's a funny looking spacecraft I've made, and the point is that it has these two rocket engines and they don't point straight. But even though they won't point directly towards the center of the circle, I can make this circle around that other spacecraft out there, which is just there to be a reference point to show that I can go in something like a circle. And so now the trick is to wait until I'm about perpendicular to the direction. Where is it? Here we go. And now if I just stay pointed roughly at it and keep thrusting, you will see that I am going roughly in a circle around the other probe. Just to briefly explain this, the rocket, there's no weight. We're way out in deep space. There's no weight force. All the rocket has acting on it is the forces due to the rocket engines, or rather the gases expelled out the back of the rocket engines. We call those forces thrust. I'll call them F sub T for thrust. And it has two of them that are at these funny angles. And the thing is that as long as I keep the nose pointed into the center, these two thrust forces add up to a force that points directly to the center. And hence, if I balance the speed and the distance correctly, this can go around in a circle.